So the question here for you is there anything, or which of these doesn't belong? Which of these integrals does not belong? So kind of like the old, what was it, Sesame Street, you know? Which one of these does not belong? My kids were playing that not too long ago, I think. But one of these just doesn't fit with the other. So, well, the last one has kind of a problem in as much as cosecant's not defined at 0. So that's kind of a problem. What else could be a problem with a couple of these integrals? Yeah, infinity is your limit on these things, right? How do you calculate, the area all the way out to infinity? Well, that's what we're going to figure out. So this one, there's nothing wrong with this one. This one's a proper integral. But the rest of them are improper integrals. Improper. And what makes it an improper integral is the limits. It could be on one end or both ends. You could have infinity or negative infinity. Or at some point, either at the limit or in between there, you have a place where the integrand itself is undefined. And if you remember, cosecant is 1 over the sine. Sine is 0 at 0, so all of a sudden you've got something which is undefined at 0. And that's a problem. So we're going to have to learn a way to work around that. And a way to work around that is to start working with limits. So let's do one that was kind of an old exam problem. And let me show you what we can do with that. It was that rocket problem from test 1 where how much work was done pushing this rocket up into space. So it was something like this. We had the integral from, and don't copy this down yet, 4,000 to 4,100 of, it was like 16 million. So I'm just going to write it as 1.6. That'd be what? 16 billion. So it's 1.6 E9, to use our calculator's notation, divided by x squared dx. But instead of going from 4,000 all the way up to like 4,100 or something like that, what if we wanted to push this out into the deepest, darkest depths of space? Find out how much this work is done just pushing it out to essentially infinity. Well, the way we're going to work this is to handle infinity. I'm going to make a temporary little replacement here. So I'm going to write that as the limit as b approaches infinity. And let's take the constant out. So that'd be 1.6 times 10 to the 9th. The integral from 4,000 to b of x to the negative second dx. So what I do, I replaced that infinite limit with, a variable, and that variable is going to go up to infinity. And I'm going to work it like this. Now, a lot of the rest of our work is going to seem the same, and it will be. It's just that when we're all done with our antiderivative, stuff like that, we're going to have to apply the limit. So let's factor out the 1.69, or 1.6 E9 times the limit as b approaches infinity. The antiderivative here is going to be negative 1 over x between the limits of 4,000 and b. Okay. So let's keep going. Let's plug in our limits and see what we get. So 1.6 E9 times the limit as b approaches infinity of negative 1 over b minus negative 1 over 4,000. Now the double negatives can cancel each other out. That's fine. So quick little fix on that one. Let's get rid of the double negatives. And now let's take the limit. Let's start with the easy part. And they're both really easy parts. The limit as b approaches infinity of 1 over 4,000 is just 1 over 4,000. This doesn't depend on b. But what happens here? As b approaches infinity, what happens to this limit? Good. So I get 1.6 billion over 4,000. So 4,000 to cancel there. So let's see. What about 4.4 E5, 0.4 E6, so it'd be 400,000. Something like that. All right, but the point is, we're able to work around having this infinite limit by putting in that little variable and taking the limit as b approaches infinity. And that's what's going to be our trick in working with these improper integrals. We're going to do that not only for infinite limits, but for limits where you have a place where the integral is undefined, or the integrand is undefined. So any of those would constitute an improper integral. By the way, you're actually already familiar with the area of, well, not necessarily the area, but the shape of something that leads to an improper integral. And that is this one. What's this one called, or what's this curve all about? Yeah, it's the bell curve. That's how intelligence is supposed to be distributed. You're supposed to have, a lot of people here in the middle, and then some people off to the left, and some people off to the right, below the mean and above the mean. People who didn't take Jeff Parent, people who did take Jeff Parent for Chicago, etc. So, all right. Yeah. All right, so let's do a couple more like this. Let's move into problem number 18. Very similar to the one we just did. So the integral, by the way, the area underneath that previous function, should maybe just mention, is really cool. It's a beautiful calculation. Kind of a messy function itself, but the area underneath this curve is 1. It's scaled to be 1. But the actual calculation of this is probably something that you can do in the next class, not here. But it's really clever, very clever. You end up having to square the integral. Let's see. So 1 to infinity of 6 over x to the 4th dx. All right, same problem as the previous one. That is, we have this upper limit, which is infinity. And we can't really deal with that. Let's replace that upper limit with a dummy variable. Out of habit, I'll use b. So the limit as b approaches infinity of the integral from 1 to b of, let's call it 6x to the negative 4th dx. 6, let me bring it all the way out in front. 6 times the limit as b approaches infinity of negative 3x to the negative, be negative 1/3. Yeah, divide by 3. So negative x to the negative 3rd over 3. And that's between the limits of 1 and b. Or in other words, 6 times the limit as b approaches infinity of negative 1 over 3b cubed minus 1 minus negative 1 over 3 times 1 cubed. And like the last problem, we're going to get something nice happening here. This term in the limit goes to 0. Yeah, because you're taking the limit as b approaches infinity of negative 1 over b cubed. So that term just goes to 0. You're dividing something constant by something that's growing at a polynomial rate. It's just going to go to 0. Yeah. Last but not least, this is a minus and a minus, so that's a plus. So I'll have 6 times 0 plus 1/3 6 over 3 is going to be 2. So that's the total area, 2. Andrew? Yeah, I could have taken it outside. Yeah, good point. Yeah, I could have easily taken it outside. I appreciate the question. One thing that I do want, though, one thing that has to be part of your problems is these limits. A lot of times people get a little bit lazy with the limits. They don't write them all the way through. This is not an equality if you drop the limits. And I get pretty uncomfortable if you start taking shortcuts like that. Because it's really no longer true if you don't write the limit in this stuff. So please do take care to write that for me, if you would. Anything else on these first couple here? Okay. Let's try another one. And I apologize if they're looking similar. I think you will find that there is something a little bit different about this one, though. And let me see if I think I have some of these graphed already. Let's see. Let's get rid of this one, at least for now. Okay. Not yet, but yeah, maybe we'll graph this one. So it's problem number 20. Problem 20. And it's y equals 4 over the fourth root of x. I'm not going to try and find the key for the fourth root. I'm just going to raise this to the 0.25 power. Now, we're trying to find the area underneath this curve between 1 and infinity. So starting here at 1, moving all the way out to infinity, is there essentially a finite area underneath this curve? Well, we'll find out. Let's switch over to here. The integral from 1 to infinity of 4 over the fourth root of x dx. So in the first two problems we've done here, we've ended up with finite answers. That means there's a finite amount of area between the curve and the x-axis in the limits that were given. See if you can at least start this. Rewrite the integrand for yourself. Try and figure out, all right, well, how am I going to rewrite this? Okay, should look something like this. The limit as b approaches infinity of the integral from 1 to b. Now, the rest of it is a little subjective. I wanted to see this limit part. You might want to take out the 4, and you could rewrite the integrand as 1 over x to the 1/4, or better yet, x to the negative 1/4. So let's rewrite that again. I'm going to take the 4 all the way out in front of the limit. 4 times the limit as b approaches infinity of the integral from 1 to b of x to the negative 1/4. This is just a simple integration now. Let's see here. That's going to be 4 times the limit as x approaches infinity. I should say x as b approaches infinity of x to the 3/4 divided by 3/4 between 1 and b. That 3/4, when you divide by 3/4, it's the same thing as multiplying by 4/3. 4/3 times 4 is going to give me 16/3 times the limit as b approaches infinity of b to the 3/4 minus 1 to the 3/4. So just dropping in the limits there. And what's that limit? Infinity. Yeah, it's infinite. So essentially what's happening is that even though this curve does kind of slowly get towards the x-axis, that is, slowly gets towards 0, it doesn't get there fast enough for there to be a finite amount of area. There's an infinite amount of area between x equal 1 underneath this curve and the x-axis and infinity. There's an infinite area. That's not true with everything. We've seen a couple curves already where there's been a finite area, and it's just going to take a little bit of work to evaluate these things and decide what's what. You know, are you getting an infinite curve? Essentially, does that area diverge, or does it converge to something? Okay, how are we looking on problem number 20? Dylan, question I can help out with? Oh, here? Okay. Okay, so dividing by 3/4 is the same thing as multiplying by 4/3. So 4/3 times that is where I get the 16/3. Okay. Liam?
I was just curious, could you have a limit for a and b?
You could have limits on both ends, sure. You know? Yeah. You could. Let's do one that's a little bit different. See what you note about this one. Problem number 36. The integral from 0 to 8 of 3 over the square root of 8 minus x dx. Is there anything wrong with this one? I mean, we don't have an infinite limit, right? I mean, we're all good here? Ah. We got to be careful because it's undefined at x equal 8, right? At x equal 8, essentially you have infinity in the integrand. So that could be a problem. Let's just take a look at the graph. So let's stitch this one. Y equals 3 over square root of 8 minus x. And let's also put in another line here. Let's do x equal to 8 so we can kind of compare things here. It's a good question. I mean, is this getting close enough to the vertical asymptote fast enough so that this area bound between these two curves is finite? Let me see if I can't make that area a little bit more clear for us. We wanted the area between 0 and 8 and above the x-axis. So y greater than 0. And let's just try and make that area pretty clear for yourselves. So here's the area that we're looking at. Is that finite enough, or is that finite? Tough to tell. It depends on how fast this is getting really close to its asymptote. So let's play around with it. We'll rewrite this. Now in this case, 0 is fine. Nothing wrong with 0. Our problem is at 8. So this will be the limit as b approaches 8 of the integral from 0 to b. I'll take the 3 out, and then I'll take it out in front even further next. That'll be 8 minus x to the negative 1/2 dx. Now it's up to you if you want and or need to do u substitution to integrate this one. You could. It gets a little bit messy because you'd have to change the limits of integration, which maybe I'd rather not. So let's see if we can't do this without that. That'd be 3 times the limit from b, or as b approaches 8. Add 1/2 to the exponent, 8 minus x to the 1/2, divide by that same exponent, 1/2. But we're also going to get a factor of a negative here. So I'll take that negative and pull it out front. 0 to b. Let's clean this up a little bit. The 1/2 is going to, dividing by 1/2 is the same thing as multiplying by 2. So that's -6 times the limit as b approaches infinity, or b approaches 8. See, I'm used to infinity here. That's essentially the square root of 8, or square root of 8 minus b, minus, plugging in a 0 here, I'll get the square root of 8. Okay, couple things to clean up. But let's start here. What's the limit? What's going to happen when I take the limit? What's going to happen to this term when I take the limit? As b approaches 8, goes to 0, right? So it's 0. So I have -6 times -√8. So it's going to be a positive 6 square roots of 8, or better yet, 12 square roots of 2. Nice. Now, your calculator has capabilities, numerical capabilities. Let's see how it does on this one. Typically speaking, with these improper integrals, sometimes it can get it, sometimes it can't. And oftentimes, it takes a long time for it to grind out. It's just going to depend on the problem and the type of software that TI has engineered to do its numerical integration. So let's see. Math 9, integral from 0 to 8 of 3 divided by the square root of 8 minus x dx. I was wondering if anyone would catch that. If you hit the alpha key, then the y equals key, it'll give you the fraction. By the way, you see that little bar, or that little ball? That's kind of like the same thing you see on like your Macintosh, that little spiral of death that says, all right, I'm thinking, just wait for me. I hate it. But that's essentially what it is. It's thinking. This is tough for it to do because you're trying to find the area near a vertical asymptote. So let's compare this to 12 square roots of 2. It's looking pretty good. Yeah. I mean, it's not perfect, but it's pretty good. At least it kind of confirms what we think to be the correct answer. Okay. How are you looking on 36? Okay there? All right. The crowd is going wild. Okay? Yes? Why? If you took time to do a u substitution, u equals 8 minus x, then your du would have a negative in it. And so I just factored that negative out. That negative would be part of the antiderivative. And rather than put it here, I just took it out front. Okay? All right. Thanks. Anything else on 36? Let's try problem number 26. So the integral from 1 to infinity of the ln of x over x dx. Now this is a good one to see because you'll run into this kind of problem later on as well. And the challenge, in addition to the improper integral, is trying to figure out how to integrate this thing. So I'll start out with all these by rewriting this as a limit as b approaches infinity of the integral from 1 to b of ln of x over x dx. This one you don't need anything more fancy than a u substitution. Can anyone figure out what we need to let u equal? Ln of x. Good. So if we let u equal ln of x, du is 1 over x dx, and we're all set here. So that's going to be the limit as b approaches infinity of the integral of basically u du. There's one thing that I've kind of left off. What's missing? My limits. My limits of integration are no longer 1 to b because I'm in units of u. I'm in a different unit. And I really don't want to mess around with a problem like this and changing units, so I put in the proper limits here. So I'm just going to go back to my original units once I find the antiderivative. But right now, if you want, you can put like r and s or something like that as just kind of a dummy variable until you're done with the integration. So that's going to become the limit as b approaches infinity of u squared over 2 from something to something. And now we can kind of clean this up a little bit. I'll take that constant of 1/2 out in front times the limit as b approaches infinity of ln of x squared between 1 and b. Or better yet, 1/2 times the limit as b approaches infinity of the ln of b squared minus the ln of 1 squared. All right, so I get a little simplification here. What's the easy thing I can do to simplify? That's a 0. Cool. Thanks, Hans. What about the rest of this? What happens when I take the limit as b approaches infinity of the log of b squared? Where's that function going? Where's the log going? Even though it kind of goes there slowly, what happens to the log? Yeah, it goes to infinity. So if you were to look at our graph, let's see, that one was 26. Let's see. So essentially, this is what the graph looks like. And what's happening is that, yeah, this curve eventually gets down really, really close to the x-axis. It just doesn't get there fast enough for there to be a finite area trapped between the curve and 1 and infinity. It's just an infinite area. So this limit, as x approaches infinity, is infinity. You don't have a finite area there. Yes? Well, if you look at what the integral represents, it's a good question. If you look at what the integral represents, that's your limits, but this really represents the area underneath that curve between 1 and infinity and above the x-axis. So it's that area that's infinite. So, and I've got that graph right here.
So an answer could be anywhere in that area.
Well, the total area is infinite, is what we're saying there. Yeah. If you cut it off at any finite point, then you're going to have a finite area. But when you try and go all the way out to infinity, that's when the integral becomes infinite. Yeah. So in any finite value, it would have a finite area. It's only when you go out to infinity that the limit is infinite. Not all of them are like that. Sometimes you get a value, sometimes you don't. You just have to do it case by case.
So by plugging in different numbers for x, you're not necessarily getting different points within that area.
Well, you could change this lower limit, and it's probably not going to change the result at all. That is, you'd still end up with an infinite area. Okay, even if you change the lower limit, if you made it 2 or 5 or 6, whatever finite number you want, it's still going to have an infinite area. The problem is going out to infinity. Now, if I made this a finite number, then I would have a finite area. But with this limit as infinity, you're going to get an infinite area. Is that what you're looking for, Ted?
Actually, I'm just a little confused. If I was to plug in, say, 3 and ln, just
You mean
say
here?
I arbitrarily took a point 3. No, not in the limit, but just a point on ln.
Well,
Over the ln 3 over 3, it would give me a point somewhere in that shaded area.
true, and
And if you use 4, it'd give you a different point.
yeah. So you could look at particular points, right here. So I think your first example was ln of 3 over 3, and it should give you. How come it's not?
I mean, would it give you a point anywhere within that shaded area?
Yeah, no, but that's the thing. It'll give you just one point. You're just evaluating the function. You're getting the y height.
Point, let's say it was
So let me just make that an equals real quick. So here we go at x equal, well, I don't know, close to 3. All right, I'm not sure.
Would the point ever be like right here?
If you go farther, if you go far enough out the x-axis, then this point is going to get lower and lower. So let me kind of zoom out this way. You can kind of see what happens to the function. It's getting lower and lower and lower.
It's really on the line.
Eventually, it gets arbitrarily close to the line. This function gets really, really close to the line. So that's why you can look at this and say, well, gee, there's a hope that there might be a finite area. It's because it does eventually get so close to 0, it's ridiculous. But unfortunately, this doesn't happen fast enough for there to be a finite area. But it does, as you're saying, get as close to 0 as you want.
Yeah, but it never gets in the white part. I mean, in the shaded part. It only goes along that line.
It'll never actually get to 0. It gets really, really close to 0.
I mean, will the y and x relationship be in the shaded area?
No,
Not on the line,
no,
but in the shaded
I did the shading. So
Okay,
if
so put it on the line.
yeah, so I mean that's the function right there. The reason I shaded it is to reflect the area that you're finding. The area that we're finding is the shaded area. So that's my shading, my doing there. So yes. So I shaded it to reflect what the integral is telling us, and it is the area that we see here in pink. And let me just zoom out a little bit. Yeah, so in pink from 1 to infinity. It's that area. Okay. All right. Thanks for your help there. No, I'm hey, that's why they pay me the big bucks.
I was wondering if you plug that in, and say it was money related, right?
Mm-hmm.
And you wanted some point in that shaded area to represent some amount of money that this equation represents. But that's
Okay.
not the case. The money's only traveling along that line. The answer is only traveling along the line.
Yeah, I mean,
You put an X, you get a Y.
there's a couple problems that it sounds like you're describing. One of them is like a linear programming problem, and then yeah, this well, if you're talking about the linear programming problems that I'm familiar with, then Yeah, the solutions are on the edges, okay? But I don't think that relates to this. So yeah, it's just an area. It's just how much area is shaded in pink.
All right, thanks.
Yeah. Okay. Let's try some more here. Um, let's try problem number 32. Since I got this open, let me see if I can't pull up 32. It's right here. I got to zoom out a little bit, and I think I've got that in a couple different. Yeah, it's here and here. So in 32, yeah, you've got a sine function, sine of x over 2 between 0 and infinity. So let me write that down for us. 32, the limit as, actually, you know what, I shouldn't write that yet. I'm getting ahead of myself, sorry about that. The integral from 0 to infinity of the sine of x over 2 dx. So it's that limit that I want to work with. Now, let's see if we can't make a prediction, because I'm trying to build up in you a little intuition as to what these integrals mean and when they're going to converge and when they're going to diverge. So if we look at this integral, I've kind of played with it a little bit. You're going to get this up and down pattern. It's just, let's see, it doesn't look quite right. No, okay, I guess it is. So you're getting this up and down pattern here. We're trying to find the area between the curve and the x-axis as x starts from 0 all the way out to infinity. Maybe, kind of, well, it's tough to say. But what's certainly clear, though, is what you're seeing, and that is this area here in green is going to be balanced out with this area in orange, right? As if you go exactly up to, say, 2 pi. But if you go up to 3 pi, well, then the area is going to be positive something. And then back to 0. So it kind of depends on where you cut it off. But what's clear is that it's just kind of going up and down. It's bouncing up and down between a positive number and 0, positive number and 0. So it doesn't look like it's actually getting to something. Let's look at what happens when we try and do the math here to confirm that. So now I can write the limit. Limit as b approaches infinity of the integral from 0 to b of sine of x over 2 dx. So it's going to be the limit as b approaches infinity of, it'll be what, 2 sine of x, or 2 cosine, no, 2 minus 2, minus 2, yeah. So minus 2 times a cosine of x over 2 between 0 and b. Let's take the minus 2 out. Minus 2 times the limit as b approaches infinity of the cosine of b over 2 minus a cosine of 0 over 2, or just 0. Now at least that last part is easy. That's just a 1. But what about cosine of b over 2 as b approaches infinity? Does that go anywhere? No, it actually doesn't converge to anything. So it does not approach a limit. It diverges. So our calculus here is kind of reflecting what we saw, and that is, yeah, the limit just doesn't really go anywhere. I mean, where does this go? It doesn't. It just keeps on bouncing up and down and never really settles down to anything in particular. Yeah, whatever. I mean, the limit is someplace between -1 and 1, but it never settles down. It just always goes up and down, up and down. It's not like a graph of, say, e to the -x, which would eventually decay towards 0 as you approach infinity. It's just going to keep on oscillating, which is frustrating for us in this particular example. Okay, let's do a couple more. Let's do problem number 70. Problem number 70 has a historical little aspect to it. And we'll move beyond just kind of our typical functions for a little bit. So let's shut this one off. Go down to problem number 70. All right. So this is called the Witch of Agnesi, and it reflects really one of the earliest female mathematicians, Maria Agnesi, who studied this curve. And what you're seeing is really how that curve is generated is by starting out with a point on the origin on this circle, and you draw a line, and you just plot really the y-coordinate of that line that you extend. So, anyways, it's the term witch in this doesn't reflect that it was a woman. It was actually a mistranslation of her work, and her work is some of the earliest surviving work by a female mathematician. So, anyways, a little historical note there for you. Let's go back and actually look at the problem. It's going to be the integral from -infinity to infinity of 8 over x squared plus 4 dx. So wow, this is everything, right? -infinity to infinity. But let's take a look at our actual graph here. Is there something we can do to maybe make our life a little bit easier? Symmetry, yeah. Yeah, this is a symmetric interval. It's an even function. So when we've run across this before, I suggested, all right, we double the integral and do it over half the area. So the integral from 0 to infinity of x squared plus 4, or 8 over x squared plus 4 dx. So that's good. And now we'll work in the limit. So let's take twice the limit as b approaches infinity of the integral from 0 to b of 8 over x squared plus 4 dx. Okay. The 8 can come out in front, so that's going to be a 16 times the limit as b approaches infinity. Any help on what the integral is? What do I get when I integrate dx over x squared plus 4? Arctangent. Arctangent of what? Good. So arctan of x over 2. Yeah, is it 1 over a? Yeah, all right, so we got to do a 2 here. Yeah, that would be right. Between 0 and b, so it's going to be 8 times the limit as b approaches infinity of the arctan of b over 2. minus the arctan of 0. Now this was kind of funny. One of these will simplify pretty nicely. Arctan of 0 is 0. The angle whose tangent is 0 is 0. But really on the other part of this, we want this. We want to know 8 times the limit b approaches infinity of the arctan of infinity. What angle has an infinite tangent? What angle? Where do you find an angle whose tangent approaches infinity? Can you figure it out with your calculator somehow? Not with cosecant. Not 45. You'd probably be best off putting your calculator in degree mode. And then let's take the arctan of ever bigger numbers. So arctan of 100, and then arctan of 1000. Yeah, there you go. So you're getting ever closer to 90 degrees. And at 90 degrees, the tangent function has a vertical asymptote. So interestingly enough here, the arctangent of infinity is really pi over 2. So overall, pi over 2 times 8, we'll get some cancellation, we'll end up with 4 pi. So 4 pi for the total area. Yay, pretty cool. Let's do problem number 50. Number 50 is going to start hinting at some general results that we're going to use later on when we're working with Taylor series and things like that. Taylor series, Maclaurin series. The integral from 0 to 1 of x to the negative p dx. Well, there could be a problem with this, and it's actually going to depend on the value of p. I'm assuming that p is going to be positive, so that's really going to put a term in the denominator. Where is there a problem then? Why is there a problem in this one? Yeah, because you have a limit of 0. If p is some positive number, then when that goes into the denominator, you've got a rational function that's not defined at 0. It's 1 over x to the power p, and at 0 it's undefined. So that's the limit we're going to have to worry about. Here, we'll live on the wild side here. I'll do the limit as a approaches 0. Woohoo! Man, scary. All right. So the limit as a approaches 0 from a to 1. Well, the rest of this now is to find an antiderivative. So let's do that. Limit as a approaches 0 of x to negative p. What do I do to find the antiderivative of a polynomial term like this? Yeah, add 1. So add 1 and divide by that same exponent. I'll write it as 1 minus p instead of negative p plus 1. And that's going to be between a and 1. So let's plug in a. So it's going to be the limit as a approaches 0 of a to the 1 minus p power over 1 minus p minus 1 to the 1 to whatever power is still going to be 1 over 1 minus p. So
This is getting deep.
so as let's see, how's that going? A approaches 0. There's something about this that's bothering me. The first one, oh yeah, I got these mixed up. I got the order here mixed up. All right, phew. So the order here is mixed up. The limit as a approaches 0, and pardon me, the order is mixed up. So this one's going to be positive, and this one's going to be negative, but it's going to be 1 over 1 minus p. Now, this is going to work provided this limit here exists, and that limit's going to exist if 1 minus p is greater than 0. In other words, p is less than 1. So if p is less than 1, then we're okay here. If p is greater than 1, then you could run into problems. You're going to diverge. Now, what's nice about some of these results is that you can start recognizing things. For instance, in problem number 54, if all I asked you is, gee, are we going to get a finite result when we integrate from 1 to 0 to 1 of 1 over x to the 1/5, you can look back here and say, all right, well, yeah, we've got the value of p is 1/5, and because that's less than 1, this is going to converge. Therefore, we'll converge. So it's a handy result, and we'll get other ones like this. Eventually, it'll lead to something called a p-test. This value right here. Let me find a different marker. There. This value right here is our value for p. And so, in the right circumstances, that is, if p is less than 1, then that interval will converge. You'll get a nice finite value. So when you integrate stuff like this, you say, okay, yeah, that'll work. You can just look at this integral and know that it will converge. Let's look at one last one, problem number 14. Problem 14 gives us the integral from -2 to 2 of -2 over x minus 1. Is it cubed? That's a cubed, isn't it? Yeah, it's cubed dx. Does this even belong in this section? Is this an improper integral? Is there anything wrong with this integral? Yeah, at x equal 1, we're going to run into a problem, right? Because at x equal 1, the denominator is 0, the rational function is undefined. So there's a problem. If you missed that, if you ignore that and just tried to integrate it, find an antiderivative, you'd end up with like 8/9. 8/9 or negative 8/9, one of the two. I think it's 8/9, which is wrong. It's just wrong. So what would you have to do like this? Well, what you'd have to do like with a problem like this is split it up. We're going to do the limit. Now, let's see. Let me break it up first as -2 to 1 of -2 over x minus 1 cubed dx plus the integral from 1 to positive 2 of that same integrand. And both of these now are improper integrals. That's okay. What you would then have to do is do both of these. Take care of the limits on both of them. You put b in here, do the limits as b approaches infinity, or actually b approaches 1. Let's just pick one of these and work on the first one. If we get a finite answer, then we'll work on the second one. If we get an infinite answer, if the first one's infinite, we're not going to bother working with the second one because infinity plus, whatever here is still going to be infinity. Yeah, well, what'll happen, it's a good question. Let's take a quick look at the graph here. So, let's put that down here. We have y equals -2 over x minus 1 cubed. So yeah, it does kind of it actually has a vertical asymptote here at x equal 1. So the question is, are these areas trapped between the x-axis and the curve going to be finite when you go from -2 to 2? It's not going to be symmetric. I mean, you can see that much. When you look at it from -2 to 2, they're different. They're going to be different areas. So we'll find out. Limit as b approaches 1 of the integral from -2 to b of -2 over x minus 1 cubed dx. All right, I think this is a good point for you to try one, and depending on how we do, maybe we can call it a night. So I'm hoping that's a good carrot to dangle in front of you. Need I repeat myself? If we all do really good on this one, maybe we can call it a night. Without you. Randy? Question? Okay, so let's take the negative 2 out in front. Negative 2 times the limit as b approaches 1 of the integral from negative 2 to b of, let's rewrite that as x minus 1 to the negative third dx. We need an antiderivative here. Approaches 1. So add 1 to the exponent, divide by the same exponent. Now the reason I can get away with this so easily is because if I did a u substitution, what would it be? It would be x minus 1 for u, and then du would equal dx. There's no constant involved. So you can just kind of do that part in your head in that nice case where du would equal dx. So that'll give me x minus 1 to the negative 2 divided by negative 2. Add 1 to the exponent, divide by the same exponent. Between negative 2 and b, we get some nice cancellation. So this is going to be the limit as b approaches 1 of, let me rewrite that as 1 over b minus, or 1 over x minus 1 squared between negative 2 and b. Limit as b approaches 1 of 1 over b minus 1 squared minus 1 over negative 2 minus 1 squared. Now the second part is just going to be a minus 1/9. Minus 1/9. But what happens to the first part? As b approaches 1, what's going to happen to the denominator? What's this going to get close to? 1 minus 1 would be 0. So you're going to end up with essentially 1 over 0, which, you know, generally speaking, we have to play around with. But in this particular case, as you get close to 1, the limit is getting close to infinity. So infinity minus 1/9 is still infinite. You have an integral that diverges. We don't have to work with the second part because if this part diverges, that is, and by diverge I mean it doesn't have a finite limit. If the first part diverges, it doesn't really matter what happens to the second part. The second part's not going to make much difference. It's still going to diverge overall. Now compare this to what your calculator would probably give you, 8/9. You have to be careful when working with these limits. And that's why I said earlier that I'd appreciate it if you're consistent with limits all the way through.
So if it diverges, it's always not have a limit?
Yeah, or it's going to have an infinite limit is one possibility. And we saw one earlier with the cosine or the sine that it just never really settled down. It didn't have a limit. So that's another possibility for us. Okay, for homework. Try 1 through 45, 53 through 57. Now a couple of these, 41 through 45 and 57 are going to involve inverse trig functions. So just a heads up on that. No, just like an inverse tangent, inverse sine, secant, that's nothing really big.